Yeah, let me erase. I will be. Actually, that's in a good place. Let's erase. Make sure. Okay. Oh no, hit it. Why does this look like? All right, sweet. Sorry. All right. So calculus 2. We are actually going to be kind of in the home stretch, starting from this lecture on, also for the semester. But nonetheless, we're kind of in the home stretch. So we're going to look at today what's called improper integrals. We'll see what's improper about them. So this is sort of another, well, you'll see. So this is, yeah, I don't know, you can call it an application of integrals. You can call it just sort of extending, us learning about integrals. But yeah, so we're going to look at what's called improper integrals. And then you'll see we're going to use that to look at convergence and divergence of sequences and series, really series. And so we kind of have like this one little extra add-on with integrals, or just kind of going forward with integrals. And then that gets us to our last application of integrals that we're really going to see in this class, at least. So convergence and divergence of series. That's it. That actually gets us there. So hopefully, right now it's Thursday. Hopefully tomorrow I'll be sending a message out to y'all in my other two classes on the final next Thursday. And just kind of you'll see in your modules as far as like when homeworks are due, all that kind of stuff. So just keep up with the homeworks. But again, the plan is, well, not just the plan. Next Thursday is the final. So I'll send out a message Friday with time slots, all that kind of good stuff. And then you'll have kind of next. I should be able to record the video of me going over the review at some point next Monday. So you'll kind of have from it at some point Monday, Tuesday, and Wednesday to kind of look at that review, and get yourself ready for that final. And then we'll take the final next Thursday. Okay. Let's look at improper integrals. So this is 8.8. And the good question, the good comment that's probably already in your mind, or is what is so improper about these integrals? So I will just start with some examples, and we'll kind of look at what's improper about that. Let's go. Right there. This is exercise 17. But more than that, let's look at, let's see. We're gonna look at the integral from 2 infinity 1 over x cubed dx. And so immediately I kind of want you to tell me what's so different about this integral. Good. So the huge difference here is we're integrating to infinity, which in some sense, I mean, one good question to begin with is what does that even mean, right? Um, but yeah, we're integrating to infinity. So that's one thing that makes integrals improper. So you've got that automatically they're improper. Improper is just a word. In fact, we don't even need the word, right? So the bigger thing we want to look at is what, you know, what is this, what issue, just basically, what does this make different about us? Or, guys, what I'm trying to say is, let's look at the situation and kind of look at, okay, if I'm integrating from 2 to infinity, what does that even mean? What does that look like? Maybe what issues does that bring up? So what I'm gonna do is I'm gonna get a graph of 1 over x cubed going. Kind of dramatize this graph because we need to see some area here. But let's see. 2, we'll do 2. So 1 over x cubed, and I am gonna focus on the first quadrant here because my integral is kind of happening in the first quadrant anyways. So let's look at the region they're talking about here. But so when you plug in a 1, you get a 1. When you plug in, say, a 2, you're gonna get 1/8. So immediately you get really low there, a really low number there, but not quite 0. So hopefully when you're looking at this, you see this as a rational function. Power on bottom is bigger than your power on top. So we're definitely going to have a horizontal asymptote at y equals 0. And then hopefully you just kind of remember graphs like this from a previous class. So should be pretty easy for you to connect that the graph of this looks roughly something like this. Keep getting closer to the x-axis. And so just that was my intention, that I should be getting closer to the x-axis. So if I'm taking the integral from 2 to infinity, so here's kind of the fun thing here. What I'm really trying to do is I'm trying to figure out area under the curve. So like we've talked about a lot, we know ultimately and foundationally, so integrals mean the area under the curve. I'm integrating from 2 to infinity. I want the area under the curve. But usually when we're trying to find the area under the curve, again, the thing that's weird about this is this would have been some number like 5 or 6 or even pi or something like that. But we would have had a place on the right where this stops. We can integrate from kind of one to the other, and we get the area under that curve. What's different here, again, symbols wise, what's different here is I'm integrating to infinity, but what's really different is what I'm saying is I want the area under the curve from 2 all the way out, but I never stop going. This graph is never going to get to the x-axis, is never going to get to 0. And so I'm going to start at 2 and keep adding up all these little small infinitesimal rectangles, but I'm just never going to stop. I'm just going to keep going. I want to say as far out as we can, but it's not even just that, it's infinity. It's you never stop. So that's really what's improper about it. With a integral, a definite integral. We're used to having a left and a right end, kind of having a stop, and this doesn't. Now, first thought then, or maybe first question, you guys, is so if this area never stops, or if the little rectangles that we're adding on never stop, then what's my area gonna be? Or would I be able to figure out the area? What do you guys think? Good. And I think it's natural to think, not just natural, it is logical, it is everything that makes sense to us that if I keep adding on rectangles, then my area is going to keep going. So I should have an infinite area under that curve. And surprisingly, sometimes it's infinite and sometimes it's not. And I'll let that kind of like sit with you and kind of blow your mind for a second. So sometimes this area not infinite. And I think the first retort, the first response to that is, how in the hell could it not be infinite? That just doesn't even make any sense. You keep adding triangles. And the answer actually ends up lying in limits. Sometimes it is not infinite because essentially, if you think of each rectangle that you're adding on, you think of it as a sequence. So I'm adding on the first rectangle and the second and the third. So as I get farther and farther out here, I'm adding on these smaller and smaller rectangles. Basically, sometimes the limit of that process of the rectangles you're adding on exists. So we saw, you've seen in I say we saw, so I'm teaching Cal 1 at the same time. So sometimes I mix y'all up, kind of what we've done with the other class. But anyways, so you guys saw in Cal 1 though, that you can have a function and x can go to infinity and the limit does exist, right? So there's maybe a horizontal asymptote or something like that, that the sequence of numbers gets somewhere. So the crazy thing here is when we're adding on the rectangles, we can think of, so again, not to spoil the next part, but so a list of numbers is a sequence, but a series is when you add those numbers back to back. And so the surprising thing is if a limit exists for a sequence, a limit can exist for a series, for numbers being added back to back, because again, basically the function that governs the sum, what you're getting when you add them up, the function that governs that, if it has a limit, then your sum has a limit. That's crazy. I want to let you sit with that for a second. That's crazy. Basically what I'm saying is the amount that we're adding on, the function that governs that sequence, or the function that shows you what that sequence is, if that function has a limit, then the sequence, the sum, has a limit. If it has a limit, that means that there's a sum. So that's kind of what we're gonna get with this, or what we'll kind of see what we get sometimes and what we don't get other times. Is we are adding rectangles on, but basically it is possible for those rectangles, that sum that you're adding to, that so you add smaller rectangle, smaller rectangle, smaller rectangle, smaller rectangle. It is possible for that sum to have a limit. Since we're going to infinity, again, thinking back to Cal 1, since we're going to infinity, the answer for that sum is going to be whatever that limit is, because that limit exists as x goes to infinity. So, and an even crazier thing is, so this seems like maybe this is just a mathematical abstract construct, right? Or, that idea is a mathematical abstract. The one thing that's unfortunate about reality is we can never really go to infinity in reality, right? Not because that process or that idea of you keep going and you never stop doesn't exist, but because we would need infinite time and infinite energy, which we don't have. But the interesting thing in reality is if we did have infinite time and infinite energy, then I say the limit exists, or I say that we have a sum here, would be really true. So like if you were gonna paint that area, you could use the amount of paint this improper integral gives you. That amount of paint would perfectly cover that area as kind of an infinite tail, right? Would perfectly cover it. if we had infinite time and an infinite energy, which we don't. So again, infinity, I think we talked about it earlier in class, or maybe I talked about it with my Cal 1 class. Infinity is really an interesting, not just concept, but yeah, it's just a really interesting idea and concept. Because as far as we can tell mathematically, it works, and it works for everything physical that we know of, that governs kind of how the universe works. However, we can never verify that stuff because we don't have infinite time and infinite energy. Again, maybe we could. It's forever. But we physically, span of our life, our species, our civilization, don't have infinite time and infinite energy. So it's kind of an interesting thing that we can basically verify it mathematically, but we can never verify it by um, call it by experiment and observation. So um, I'll throw that out to you guys. So that's kind of a philosophical idea for you to chew over. That is, like I said, it's a idea that's still chewed over in science and mathematics because we don't have a way kind of test it. Yeah. Anyways, okay, so the claim here is that it's possible for this area to actually get somewhere, basically, to have a limit, to actually exist. So how do we know whether it does or not? Again, intuitively, if I keep adding rectangles on, the area should be infinite. And sometimes it is. Sometimes it exists. So the nice thing about this section that I'll say is basically the way we test this, we just go ahead and do the integral. And because we have this infinity, essentially for one part of this integral, we're going to end up doing a limit. And if the limit exists, then it exists. The words for that is converges. So if the limit, we'll see if the limit exists and we get a value out of this, we say that the area under the curve or the integral converges. If it doesn't exist, we say it diverges. Science. Yeah. But how do we go about figuring this out? Nothing different than you've done so far. We're just going to do the integral. Since we're plugging in infinity for one of our boundaries. So we're essentially, when we plug in infinity, we're essentially doing a limit. We got to figure out the limit as x approaches infinity. So let's do an example. Let's look at it here. So the first thing is you just want to do the integral. So I'll have, yeah, actually, I won't even have you guys pause. Just take a second. I'll kind of pace back and forth. Go ahead and do the integral on this. Let's see what we get. All right, so when you integrate this, this is an x to the -3, so you bump it up to -2, divide by -2. So we're gonna end up getting -1/2 x -2 power. Or I'm just gonna be 1 over x squared. So let's just make this -1 over x squared, and we're gonna evaluate that 2x squared, sorry, from 2 to infinity, from infinity to 2. So the first thing I'm going to do is I'm going to plug in infinity. So again, in Cal 1, when you did limits, you used, this whole broad notation. The limit as x approaches infinity and all that. We're doing the same thing here, but my notation is going to be a shortcut. So I think shortcut here. So this is going to start out then -1/2 x squared, but this x is going to go to infinity. So the x is going to go to infinity. Then it's gonna be minus a negative, so plus 1/2 times 2 squared. But as x goes to infinity, what is this what does this whole thing go to? This whole thing goes to 0. If x goes to infinity, that goes to 0. And that gives you 1/8. So you get 1/8. So the limit exists. The limit for this is 0. So we end up with a calculation out of this integral. And what I'm saying is that means that this area, the area under the curve, is exactly 1/8. If you had 1/8 of a liter of paint, and this was in sufficient units that match that, and you had infinite time and infinite energy, you literally, if you capped yourself at 1/8 of a liter of paint, started painting, infinite time and infinite energy, then you would use exactly 1/8 to paint this area from 2 out to infinity. Okay, so the integral here, so the limit exists, which means the integral exists, which also means that, so on some of these problems, they're gonna ask you whether it converges or diverges. That means that this converges. But more importantly, the area under the curve is 1/8. So it works. Again, hopefully let that blow your mind for a second, not just for a second, but blow your mind for a while in this life. Um, that is just crazy. Which hopefully when you learn about limits at the beginning of Cal 1, you also let it blow your mind for a second, and maybe still blowing your mind. That we can figure out the end of a sequence, a series or a sequence that goes out infinitely. That also is just a crazy idea, but true. We can verify it mathematically. We just don't have infinite time and energy to play it out in the world, realistically in the world. All right, so they ask you the integral from 2 to infinity of 1/x cubed, or the area under the curve. And in this case, it exists. We're good. Now, very well. Let's do, so yeah, let's look at this problem. So I'm actually going to take the same curve we just looked at. This time, let's do the integral from 0 to 2. So this time, let me just reproduce this graph really quick. So this 1/x cubed function, we also know that it has a vertical asymptote at x equals 0, because you get 1/0 there. So again, I'm looking at the same curve. But this time, what I'm doing is I'm going from 2, but I'm going back to 0. Now notice that this integral has, there's nothing there's no infinity in this integral, so it isn't improper because of, for the same reason as the last integral, or like it doesn't have the same, it's not improper because there's an infinity there. But notice that um, because the x-axis or the y-axis is a vertical asymptote here, and one of my limits, one of my boundaries that I'm integrating from is a vertical asymptote, then graphically, if you look at what we're talking about, so we're cutting it off from 0 to 2. So from here to, you notice, because we have a vertical asymptote there, still end up with the same situation where we have sort of this infinite tail. So as you get closer and closer to 0, basically the rectangles are going to be larger and larger and larger, and just get huge, basically, right? And they're going to keep adding on area to my integral, but they're going to keep adding it on infinitely because this line gets infinitely large as it gets close to x equals 0. So even though you don't see an infinity here, this is an improper integral because, again, the area that you're looking at essentially has an infinite tail. It's an infinite part to it. It's just that this has an infinite part to it because you're integrating right up to not a vertical asymptote. So overall, that's what makes an improper integral, is graphically what you're always going to see, and fundamentally what we're looking at with an improper integral is you're integrating over some area that has sort of an infinite tail or peak or whatever, but just has an infinite part to it. And if it has an infinite part to it, that's an improper integral. Can't, basically, we physically can't add a bunch of things together infinitely. But what we can see is there a limit to what we're looking at? And if there's a limit to what we're looking at, then the area under that curve or in that infinite tail still exists. And therefore, improper integral exists, and we say it converges. So let's see here if we get the same thing. It's the same function going from 2 to 0. 0 is again a vertical asymptote, but it produces the same effect, gives me an infinite little area. Let's see if we get the same thing. So again, when you integrate this, so part of this is intentional. We already know the result of this integrating. It's -1 over 2x squared. We're going to integrate that from 0 to 2. When you plug in the 2, get -1/8. Notice what happens when we plug in the 0. So it's going to be minus a minus, but when we plug in the 0, so this is 1 over 2 times 0 squared. And so what is that going to give me? Good, that's going to give me 1 over 0. And 1 over 0, one way to think about it is it doesn't exist, but another way that we think about it in our calculus classes is that actually equals infinity. So this actually goes to infinity. So you end up with -1/8, but then plus infinity. And what's -1/8 plus infinity? That's infinity. So this area doesn't exist. But at least visually it might make some sense. It's like we keep getting these taller and taller rectangles that we're adding. So it's kind of like you keep adding something larger and larger, which is definitely, you're just going to keep getting more and more without end, without bound. So at least physically it might make sense to you, but honestly, I think me looking at this the first time and hopefully you looking at this, hopefully it doesn't make sense. So on one side of the curve from 2 to infinity, this existed on adding smaller and smaller parts. But from 2 to 0, the area doesn't exist, adding larger and larger parts. So literally, like I said, if you were carrying a paint can, you had infinite time and infinite energy. You could paint everything from 2 to out to infinity. Because there's a limit, there's a certain amount. But you could not paint everything from 2 to 0. That's crazy. So hopefully, again, hopefully it blows your mind, just for a second, for a while. But again, mathematically, not only mathematically true, we can verify it, so it's true. So here, the integral gave us a solid amount because this overall, it's a good notation, goes to 0. But here, the integral doesn't exist because this overall goes to infinity. So when they ask for this integral, you're going to say infinity. And they're going to ask, they might ask whether it converges or diverges. You're going to say that it diverges. So the area under the curve of this integral, this improper integral, is infinity or doesn't exist. Diverges. And that's actually going to be your tell every time. Either if it exists, when you do the integral, you're going to get a value out of it. Limits, all your limit work here is actually going to give you something. Basically, you're going to get a value out of it and it converges. If it doesn't give you a value out of it, if your limit work takes you to infinity, then area is infinite and diverges. And it is as strange as this sometimes. In the same curve, we just picked at different spots. And it didn't work. It doesn't exist. All right. I want to give you guys actually, we'll kind of give you guys, I think, 2 problems to do. So this really is the nuts and bolts of it, as far as technique, as far as mathematics, like this does the thing. You really got to trust, basically, you got to do the integral, then just plugging in infinity or whatever numbers you're plugging in, you got to trust the limit work and the calculations, and it'll tell you whether the area exists or not and what it is, whether it converges or diverges. So let me grab 2 problems for y'all. Swivel the camera here. I want to give you guys basically some problems that are just going to take a little less with the integrals, not because, so you guys can easily do the problems that take more, but more because we've already done that a ton. I know you guys know how to do that. So let's just focus on sort of moving through a problem, tell whether your integral exists or not. So we'll give you guys. Oh, we're gonna look at 19. Just the integral from 1 to infinity. 1 e over the cube root of x dx. Dx. We'll also do we'll get 37 as well. Integral from 0 to 1. Actually, give me a second. Maybe I should mimic. Maybe I should mimic what I did on the last problem. Actually, yes, to make this even easier. Let's do the integral. Let's actually just take, so we're gonna take 19 and just use the same function. We're gonna do the integral from 0 to 1. It's gonna be 3 over cube root of x dx. Sure, I didn't get in over my head on this, but so actually, in some sense, you'll see, or just even you can even think about it visually, kind of a similar setup. So we have 3 over cube root of x. Ultimately, cube root is a power function. So this graph is also going to look like, overall, this graph is going to look like our last graph, just maybe less steep. And so we'll get to that. We'll get to a picture. But so we have a similar looking graph. Again, one part I'm doing 1 out to infinity. The other part I'm doing 1 back to 0. So I'm either doing solid number out to infinity, or I'm doing a solid number back to what, again, in this case is going to be our vertical asymptote. I think before I set you off on these problems, let me just go ahead and graph these areas just to sort of emphasize that point. So in this graph, so again, like I said, this is really x to the 1/3. So this is again, what do you call it? Essentially a rational function, not quite, but same thing really. So essentially a rational function. We have a vertical asymptote x equals 0. We have a horizontal asymptote at y equals 0, because the power on top is still less than the power on the bottom. And if we count this out, let me just. It's like I said, it's just actually pretty much the difference is it is not as steep. 6, 7, 8. So let's see, it is 3. Then next time I can take the cube root is all the way out at 8. That's 3/2. So this graph kind of comes in like this with a very gradual curve towards the x-axis. And on this first one, we're gonna evaluate it from 1 to infinity, so I want that area. Second time through, I'm gonna evaluate it from 0 to 1, so I want this area. So I'll draw that again. That's a 3. 8, that's a 3/2. The second time around, you're looking at this area. Same kind of setup, and let's see what we get this time. So so I'll go ahead and have you guys pause on your side, pause on my side. I'll pause on my side, work both these integrals, and let's see what we get out of it. All right, let's see what y'all got. So here, doing the integral. So this is really x to the -1/3 power, right? So doing the integral, -1/3 bumps up to a 2/3. Then you divide by that, that makes it 3/2. So the integral of this, you should have got 9/2 x to the 2/3. We're going to evaluate that here from 1 to infinity. We're going to evaluate that here from 0 to 1. Let's see, for 1 to infinity, let's see what you guys got. So notice for 1 to infinity, you would have had, so again, 9 x to the 2/3, but this x is going to infinity. If the x goes to infinity, what does this piece overall go to? This whole piece goes to infinity. So infinity is big, infinity is strong. So you may be taking a cube root and squaring it, but it's still going to keep going up. So this whole thing goes to infinity. Now the second part is nice. You end up getting basically 9, but infinity minus 9 is still infinity. So this still diverges. So this area that you're getting, these rectangles, these smaller and smaller rectangles, this one's going to go to infinity. So comparing it to 17, almost one way to think about it is essentially these rectangles, they are getting smaller and smaller, but they're large enough that it's still, in some sense, it outpaces any type of, the reason they use the word convergence, when you think of convergence, you think of two things meeting each other, right? Or like hitting, hitting equal levels with each other. So it sort of outpaces any sort of convergence, any sort of ability for it to to yeah to converge down to a sum, to an amount. So on 17 it worked, it converged and you got a sum. On 19, same, like I said, so part of the reason I did this particular problem, essentially the same diagram, right? The curve, the shape is slightly different, but essentially the same diagram, same part of the diagram, from a number out to infinity, but this time it didn't work. This time it doesn't work, whereas with 1 over x cubed it does work. So when we get into the next several sections about convergence and divergence of sequences, or sorry, series, you're going to see this idea come back. Because essentially the difference here is the powers of x, right? So one was a third power, one was a 1/3 power, if thinking about it on the bottom of fraction. So there might be an idea of basically, is there a largest power, or is there sort of a threshold? What power would you need on the bottom so that any power above that, if you got x to a power, any power above that, it's going to converge. You're going to be able to get an answer for the area here. You get an area here. Whereas, so any power below that, it diverges. Basically, the power is too small for this area to settle down. You get an area. So that might be an idea that you're kind of rumbling over in your head then, because we're noticing kind of pattern here, or at least sort of dichotomy in behavior. The x cubed was enough for those rectangles to kind of settle down and give you an area, whereas the x to the 1/3 wasn't. So is there a break line? Is there a break even line? Is there a certain power that above that power it's always going to converge, and below that power it diverges? And talk about that. Uh, next time. But this diverges. Then going to the integral from 0 to 1, you plugged in the 1, you should have got 9/2 out of that. And when you plugged in the 0, what do you get out of that? You get a nice crisp 0. This is 9/2. So this area does exist. They do exist, sorry, old commercial. But this area does exist. Again, if I had a paint can and I had infinite time and energy, I would use exactly 9/2, whatever, volume unit we're using, 9/2 liters, to paint this area under there. The area ends even though the space doesn't end. Again, just let that not just blow your mind right now, but blow your mind for a long time in this life. That it's just weird and crazy. Yet we verified it mathematically. It does work. So I don't know, but yeah. Again, like I said, that philosophical comment that I made, leave you to debate that back and forth in your head. Debate that in hallways, with a friend or with another student, etc. Like that's some fun thoughts. That's a fun debate, and that probably have that debate for a long time. All right. So this area does exist. So this converges. Good. All right. Most of your examples are going to look like that. I want to look at one other example. So let's actually part of the board. Yeah. Let me just erase what we just did here. So give you a second. Make sure you have that. I'll pause the video and write it down. Then let me go ahead and erase this, and we'll do one last problem. So again, almost all the problems in the section are going to be like this. So no matter how complex that integral is, so the fun thing is, I gave you some problems where you could pretty easily visualize the graph of it. But the fun thing is that, again, no matter how complex this function is, even when you can't visualize what that area looks like easily, you can still just play this out. It's still the same two fundamental results. You're either going to infinity or you're going to a solid number. But either way, when you plug things in, either your limit exists, there's an area, or it doesn't, and there's an infinity. And so you're gonna get the same results no matter which problem you're looking at, no matter what those functions are, no matter, again, the key is whether you can visualize that graph very well or not. So, and that's kind of the cool thing is, you just do the integral work with the limits and it tells you whether it exists or not. All right, so then the last thing I want to look at, again, we'll use the function. So we'll go back to 15 actually. Especially because they already give you the graph there. Not that I don't want to be awesome and come up with these graphs every time, but it is nice. One, that I could just draw the graph that they have there. But two, that you can use that as a visual reference. So we're gonna do the integral from 0 to 2. This time it is 1 over x minus 1 squared dx. So there's no infinity here. So you would figure then that one of these is possibly our vertical asymptote. But I do want you to take a second and think about it. And again, you can see it on the picture, but just think about it from the rational function 2. Where would my vertical asymptote be? Good. So again, vertical asymptotes what happen when you have solid number divided by 0, or non-zero number divided by 0. And what makes the bottom 0? Good. That would be 1. So notice that neither of these numbers are a vertical asymptote. What's happening is the vertical asymptote is actually in the middle of the area that we're trying to figure, that we're trying to find the area. So like they've drawn there, let me just reproduce this. But my vertical asymptote is actually at x equals 1 here. And so what we get, so we're going to get a curve like this coming from the left side. And then we're also going to get a curve like this coming from the right side. And we're going to cut up our region at 0 and 2. So what we're doing then is finding the area under the curve. But you sort of have, so the interesting thing is though, even though again, the vertical asymptote is not some physical boundary here, you sort of get this infinite part to the left and we get this infinite part to the right going up. So we want, well, I meant to make these the same gradient or the same direction, but we want the area total underneath that. So we're essentially, we got this kind of cool odd shape that has this infinite, I don't know what you want to call that, an infinite spout that just keeps going up and up, because in reality it's sort of going infinite on either side of this little invisible vertical asymptote. And they want you to find the area in this region, including that vertical spout, kind of through that vertical spout or infinite spout. So if you get a situation like this, the one thing to kind of realize is, again, the infinite is happening kind of because you're going up against this vertical asymptote of 1. Also realize that because there's a vertical asymptote at 1, remember that the graph doesn't actually exist at 1. There's sort of this phantom little zone there, infinitesimally small, but still, again, not just mathematically, but realistically true. The graph does not exist on that little dotted vertical line. So what that means is this area looks like, again, if you saw this as a piece, manufacturing piece, it would look like one whole contiguous piece, but it is really two pieces. It's the piece to the left of 1 and it's the piece to the right of 1. So what that means then for our area is you've got to break this into 2 parts. You've got to do the integral from 0 to 1 over x minus 1 squared dx. And then you've got to add on the integral 1 to 2 of 1 over x minus 1 squared dx. Because again, the graph doesn't exist at 1, so we basically can't pass through. We can't integrate all the way from 0 through to 2 because we can't pass through 1. Go up to it, but we can't pass through it. So again, the visual then tells you that you have to split this into 2 parts. So in order for our area to exist here, notice that means that this area's got to exist and this area's got to exist. So again, we're gonna get either converges or diverges. Either the area is or the area isn't, and it's infinite. So again, either it's a number or it's infinite. But here, the interesting thing is it could be infinite because it could be infinite because maybe both of these. So let's say the result is infinite. This is an infinite area. There's a couple ways couple reasons it could be that. Couple ways it could fail. It could be infinite because this one's infinite, but not this one. So this one could give you a solid number, and this one could be infinity, but infinity plus a solid number is still infinity. Or vice versa. This one could be infinite, and this could be a solid number. Infinity plus a solid number is infinity. Or both could be infinite, and definitely infinity plus infinity is infinity. So if you think about it, what's the only combination that makes this area exist, that makes this integral converge? So if any one of these are infinite, this thing diverges, it's infinite. So the only way it works is if both of these exist. Both of these have to give you a solid number. Both of these have to converge. But if you get that, then it's good. You have an area for this. And again, you could take a bucket of paint with infinite time and infinite energy, and a certain amount of paint will be exactly as much as you need. All right. Okay, so a lot of talking. Now let me have you work this. So go ahead and pause on your side. I'll pause on my side. Go ahead and work these, and let's see if this exists or not. So when you integrate this, so x minus 1 squared, x minus 1 to the negative 2 power. So that's a little bit of substitution, but not even really. So negative 2 power bumps up to negative 1, and you divide by negative 1. So you're gonna end up with negative 1 over x minus 1. And again, the other part of this is, like I said, it's a little bit of substitution. You should also divide by the derivative of x minus 1. But what's the derivative of x minus 1? That's a 1. So we're gonna evaluate that from 0 to 1. And then the integral on this ends up the same way, negative 1 over x minus 1, and we're going to integrate that 1 to 2. And what you should have got on both of these, so for instance here, plugging in 1 gives me 1 over 0, but that's infinity. Now 0 is nice enough. 0 gives me, I guess it's really technically a minus 1. Minus a minus. 0 minus 1 is a negative, so minus 1. And then if that wasn't enough, if you go ahead and go over here, the same thing happens. So you end up getting negative 1 over 0, which goes to infinity, or really negative infinity, I guess. And then 2 gives you a 1 here. But either way, we end up getting, actually, so I'll say these are actually technically negative infinity. Either way, we end up getting negative infinity out of all this. Which means my area, well, actually, I guess we're out. Never mind. Not inundate you with guys with some theory behind infinity, but so we'll just call it infinity. But either way, we get infinity, which means the area is infinite, which means this diverges. So infinite diverges. So again, this works. So you do have to be careful. You do have to look at where basically your vertical asymptotes are. Your discontinuities. This technically applies also to. I guess it would apply also to holes in the graph where you get 0 over 0. But so you do have to be aware of where your discontinuities are, and if your limits of integration go over that, then you got to split it into 2 pieces. So again, you got to have some visual of these. But even, yeah, but otherwise, this works every time. Just do the integral, and if it goes to infinity, it diverges, and if you get a solid number, it converges. All right, good stuff. All right, that'll get you guys set up well for this homework 8.8. I will see you guys on for the next lecture.